happened yesterday. We lost.
So meantime, show of hands. How many people have used large language models?
There is a button. There is an option here. Where is the
How
mouse?
many
Mouse
people
is
have
here.
heard
Okay.
about large language models?
We need to stop the sharing and then
Okay.
go there.
That makes my life a bit easier.
Okay, my mouse is here.
Burgert used to do this survey about machine learning, the thing before large language models. And I
Let
remember
me-
my first year of
You
PhD,
just want to
when I
explain
was
this
in lab.
presentation, right?
The show of hands was about of maybe, I think there was 150 people in the room, about
Is it
5 to
this
10
one?
would raise their hands.
Yeah,
The
but
year
then
afterwards it
because
was
of being
20,
duplicate,
and the year after that it was probably because of computer
No.
vision
even the same
around
screen like
100.
before. Even
So
the setting before.
it's really from one year to the other one. The
Yeah.
community has become aware of the machine learning phenomena in general, and then this is good. Thanks. Yeah, thank you. And then over the last couple of months, because we're talking about January, they've become familiar with the concept of large language models. Yeah, amazing. Thank you. All right, so we're there.
So the same screen.
Okay, awesome, thank you. Yeah, and so because I'm kind of lazy, I have not finished my PhD. I'm a really bad PhD student. No, this is perfect. I am lazy and I have not prepared a presentation, so I just have someone else prepare it for me. This is literally what we're going to talk about today, I suppose. Large language models are the next pocket calculators. And instead of me talking about large language models, I let large language models talk about large language models because they know themselves better. And this is sort of like a running gag that I have. I did it a couple months ago, it worked really well. So let's see what comes out. And the fun thing about this is it sounds ridiculous, but it works. And so they give you a nice title, which is not the title that I gave it, right? The mergers of large language models, of exploration of the potential application and future implications. I didn't say any of that. I mean, you saw what I inputted. I inputted large language models next pocket calculators, and they came up with introduction, large language models, NLP, AI application, high quality language output, which is true. They can create convincing language, they can create convincing image, they can find meaning in images and suggest images, which in this case, I mean, maybe the image is not as suggestive of large language models, but it's topical, right? It's text messaging, it is a phone, it's smartphones. Application of large language models, chatbots. So we know this is ChatGPT, Bard, the models coming out from Meta, from Facebook, and other applications, of course, also in biology, which, as I said, I'm not going to talk about today. Language translation, search engines. I mean, obviously, the prominence of ChatGPT is not only because of ChatGPT itself, but it's also because of Microsoft's acquisition and Bing search. And I have a fun slide I actually did prepare a presentation and I'm going to show it, but I have a slide on that on the presentation as well. Yeah, they can increase productivity, they can steal jobs. That's obviously not true. They can increase the way we increase, not the efficiency necessarily, but just the way we approach certain tasks. So for instance, creating a presentation for large language models. Challenges of large language models. Oh wow, they know about their own challenges. Bias, privacy, security, computing power. I may know something about those issues. And there is also a conclusion, and you can definitely not reach me at this phone number because it's not mine. But yeah, you do. You do see how these things are quite interesting. And again, all I inputted to this tool was just this title of the presentation, and it spit out about 10 slides talking about large language models in a convincing way, with graphics, which is not to be understated. All right, and so I want to try my French here. Okay, just press this button. All right, so over the last 12 months, people have used Google mostly to search for ChatGPT. This is quite interesting because it used to be that you would buy a Windows computer and then you would have Bing pre-installed and you would Google Bing or Bing Google. And now you sort of like do the opposite, being that ChatGPT at least is part of Bing search. And I'm supposed to talk about the introduction of large language models, and I thought it would be a good idea to just talk a little bit about the history. So there are some key steps, I would say, in the development of what we see in ChatGPT and other systems today. The first foundational one was the attention mechanism. This famous paper with an incredible title, "Attention is all you need," and it really is true. Attention is fundamental in the way we approach language and other sequence data. And what we see here is just an attention mechanism. So if we have a sentence, where do we put the attention of the words on those sentences? And so in this case, different words have a certain attention put to the word ball in the sentence. And this stems from the transformer model, which you see on the left, which is, in this case, a transformer model is an umbrella term for models that may be encoder or decoder. The idea of encoder-decoder is, as the name suggests, one encodes a certain input and the other one decodes, and the representation in between, which is also called representation learning, the process of learning these representations, is some abstract representation in numbers of a meaning that you put in, and the meaning could be a sentence, right? Then we applied this to natural language processing. So we created new models, architectures, to learn representations of text, but also to generate text. And so one example of this is BERT, which was invented by Google. And the other one is GPT, which was pioneered by OpenAI. And so these models take the transformer architecture apart, and they leverage one of the two sides, for instance, may leverage both. So in the case of BERT, they're only using the encoder. In the case of GPT, they're only using the decoder. Why is this important? Again, with the decoder, there's this sentiment of generating. With the encoder, there's this sentiment of representing. All right, and then another thing that happened is we went from language models to large language models, the first L of the equation. And this vastly outpaced Moore's law. So for those of you who are computer scientists, there's a law that states that the number of transistors doubles every 2 years. This law is not active anymore, let's put it this way. We can't double the number of transistors because of physical limitations, but the number of parameters in language models is more than doubling every 2 years. And so we see some curves here about some of the famous language models that have made it into the public. And the adaptation of these larger models, the rationale behind incrementing the size also has to do with the fact that we need to increment the hardware. So we need better hardware to train these models. And we need to have better software for it as well. So there's a lot of abstraction in just the software and hardware layer in order for people to just go out there and say, I want to train a larger model. And we are today in a situation where you can go out, train your large language model with just a number of small tweaks on openly accessible libraries from a variety of different companies. The next capability which emerged once we started scaling large language models, apologies, to large language models, are these few-shot and zero-shot capabilities. And this is really what prompted ChatGPT. And what we mean with zero and few-shot is that you, in the traditional machine learning sense, always needed to have pairs of observations. So you had some input and you had some output and you had validated it. And with zero-shot and few-shot learning, you don't necessarily need that many examples for the models to be able to make sense of the problem that you're trying to model. And so just by asking questions, the model is able to give you reasonable answers for some of the problems. For other problems, for instance, in the few-shot learning case, you may guide the model by giving it a couple of examples, and then it's able to generate better responses. So this is an emerging capability which led also to ChatGPT. So there's just an animation here, but it's not readable. So, and then lastly is actually the productization. Sorry, too complicated. It's making the large language models a product, which sounds trivial, but it's obviously not. I mean, that's why we talk about AI and not about machine learning anymore, because these are not just machine learning tools. They're machine learning tools in a setting. So if you go to ChatGPT and you ask certain questions, it's not going to answer all of them because there are checks and balances in place, which are software solutions for you to not go into certain corners of the language model, which may be toxic or maybe biased. And so what we see really is is an interface. That's also an engineering effort. And we see an interface, we see some software engineering behind, which guides us towards how we can use the system. And so that is quite important. It's interesting. It means that if you take a language model, a GPT-4, for which there is an API, and you should try to adapt it to your problem, yeah, you're going to get something out of it, but you also need to take into account that if you have to make a product out of this, you actually need to consider what are the product needs in your case. Right. And so large language models are not just for text. So we do have examples for images. Stable diffusion is a famous example for that. There's also imaging by Google Research. There's Whisper, is a model by Meta, OpenAI, apologies, for audio generation. I had an example, unfortunately, because of transition to PowerPoint, I cannot make it. But I was chatting with Steve Jobs about protein language models. It was quite surreal. And then we can apply these models also to entities which are interesting, maybe to some of the people in the room. For instance, chemistry. And I didn't mention protein, so I did my job. All right, and so just to go into large language model development, to introduce a little bit the technology behind, it feels prohibitively difficult as a problem if you just look at the research and you go to nearest papers. I mean, there are all of these things like parallelization of the training, how do you efficiently distribute this on multiple GPUs and multiple nodes, there is which architecture to use. It's just complicated if you approach it from a scientific perspective, not being in the field, but luckily it's a software engineering enterprise today. And so you can approach it just as a user, and you can go out and use open source resources. And I'm going to focus mostly on the language modeling part, just to give you the concept of what these models do and why people shouldn't be so scared about them. But there are basically 4 steps to the development of a large language model. Well, first is the data processing. You actually need to be able to produce some fairly large data sets of the things that you want to learn. This needs to be self-supervised, so it needs to be data set that is just, it doesn't necessarily have annotations, it's just a rich data set of primary data, like text. Then you train your large language model or your large transformer model, as it probably is more accurate. And you may have some downstream tasks, so things that you want to predict, things that you want to generate. And then you have to put it into deployment, which is, as I said, is another software engineering enterprise exercise. But just in general, the way GPT works, and these are the models behind ChatGPT, clearly, and some of the other generative models that we see out today, is fairly simple. We have something which we call a prompt. This is a set of different words. We tend to call them tokens, technically. Tokenization doesn't quite happen at the word level, it happens at the subword level, but just for the sake of simplicity here, let's imagine that those are 1, 2, 3, 4, 5, 6 different tokens into a prompt. And then the model, which is this large language model, is supposed to predict the next token, the next word. And that's really all it does. So when we also talk about prompt tuning, prompt learning, prompt da-da-da-da, it's all about that first part and the output of it. And so here, it's going to take one of the words, garden, and then the model is supposed to guess an next word. And that's all it does, constantly. It does it for thousands of sequences. It does it for thousands of training iterations. So it sees the text many, many, many times, and it's just supposed to predict the next word. And then once we have trained the model, what we can do is we can start asking it questions, and you would think, oh, I'm asking it a question, so it's going to give me an answer. But in reality, it's just predicting my next word. So if I put my prompt into something that seems like a question, it's going to answer me with something that sounds like an answer. And so here the prompt is, would you say this movie review is positive or negative? I love that movie. And then obviously it has the choice positive, negative, great, awesome, etc., etc. It's going to choose what is most likely the correct next word. It's probably positive. And this led us to actually realize that we can do prompt engineering. And so when we're talking about jobs being lost, this is a job being created by large language models. There are people that are specializing in prompt creation. And there's ways in which you can hack the text that you put into large language models to produce better answers. Similarly as to how we became used to Googling things, now we are becoming used to prompting large language models. And you can see here that just moving from in to at in a sentence like X plays in Y position or X plays at Y position, you get an accuracy gain of 23 points, percent, apologies. So there are a couple of tweaks you can do with your prompts just to get better results, which is quite interesting. There's another inherent advantage of using these models, which is the representation aspect of transformer models. And so we can take a sentence, we can take this intermediate representation that the language model produces. These are numbers, it's vectors, it's just math. And then we can input that representation, that vector, that matrix into a separate network, fit-for neural network, another machine learning network, whatever you prefer, or it could also be unsupervised, so it could just be clustering. And we can ask that subsequent tool to give us a prediction about the sentence that we put in. And this is what we often do in computational biology and bioinformatics. And so here we see the representation of I love that movie, and then we just see the prediction of positive. And then there are many, many ways in which we can tweak these models. So for instance, instruction fine-tuning. This is the case where we have a couple of examples, as I mentioned earlier, and we fine-tune the model on these examples. Actually, we don't actually change the weights of the model, but we just give it a couple of examples, and then we ask it the question, and then it will become better at giving us answers. And there are many, many others. There are systems where we actually tweak the model itself to give us better answers to the questions that we have, many of which are popping up over the last couple of months. Just to give 2 words about the complications here. Large language models are large, unsurprisingly. So to train this, you need 2 terabytes of GPU RAM. That's something you may have if you buy a lot of GPUs. And then the math that you have to do is fairly linear, is how long is it going to take you to train this large language model, which you see a table here. And it's not just true for training, it's also true for inference. So when you actually want to use the model, you get into a similar situation where you need a certain number of GPUs. So this is the limiting factor really when it comes to using or training or doing the large language model work. But you can start small. There's plenty of people that start small. We start small. I'm in a fairly large team. And we usually start with very small parameter models that fit onto a single GPU, an A5000. We just basically see what are the model choices, the parameter choices that work, and then we scale it to the larger clusters. So it is doable also on smaller GPUs. And I only unfortunately had short time to introduce you to large language models and to a little bit of technicalities behind, but luckily a lot of my very smart colleagues have prepared many introduction lectures, many of them for free. So you can just go if you're interested in the topic, and they're going to give you a hardware-based overview, a software-based overview, a application-based overview. So there's many different ways in which you can look at the problem. And that was my intro. Thank you.
Thanks, Christian. That was a perfect intro. Thank you so much. Questions? So I'll ask a question. One of the major issues, is this on? One of the major issues, okay, go here. One of the major issues with large language models, not in bioinformatics, I think, but in general, is hallucination. It's not in bioinformatics because we have hallucinated all the time. So for us, it's not new, and we also know how to go about interpreting the results, which means we don't trust them. But in general, there seems to be a dire need to put logic in these models. What kind of a challenge is that?
I mean, this is the super interesting problem, right? So I think, as I was mentioning, we do have this large language models for training, and this is the machine learning part of the large language model. But then there is the software enterprise that comes afterwards as turning it into a product that is creating guardrails. For instance, we have a software solution called Guardrails, where you can guardrail the system not to hallucinate into certain directions, for instance, or to only respond to certain topics. This is a super important problem to solve. The issue that I see with it is that we're making these models available publicly, and there's a lot of different expertises out there, and we don't quite address all of the expertises with enough depth. So I could ask Steve Jobs about ProtBERT, which I did, and Steve Jobs proper answer was Bonnie Berger created the model, which Bonnie Berger created a similar model, but she didn't create Proper. So I think it's an interesting problem to solve scientifically. How can we, with all of our different communities, we're talking about bioinformatics here, but there's physics, there's history, there's literature. How can we create teams that guardrail the systems to create better answers and not hallucinate?
No question? Please, I encourage you to ask questions. Okay.
Thanks for a really nice introduction. My question is regarding the inference part. You mentioned that it also means high compute inference as well.
Yeah.
And from traditional deep learning, sometimes we think that it's just like multiplying weights. It might be quick and in action. So why is that?
It is still multiplying weights, but the problem is that even just the number of parameters in the model, if you take out the optimizer and everything, you still have a large number of parameters. And so even just the model itself doesn't fit into a single GPU. And then if you start adding the fact that you want to do batching, because maybe you want to be efficient, right? Can you fit the batch onto one GPU? No. So you need to start to be able to distribute those things around, yeah. So just the sheer size of the parameter, the number of parameters is prohibitive for a single GPU, yeah.
Great, thank you very much. Nice introduction.
Thanks.
Somewhere in between the training and the productization,
Thank you.
there's this thing, that's often called reinforcement learning from human feedback.
Yes.
Could you talk a little bit about that? I think it's important.
Yeah, absolutely. So this is sort of like the part where I was mentioning, we need experts to be able to tell models whether what they're producing is garbage or hallucinations or factually incorrect, right? And we usually do this by means of humans going over the text and assigning in the simplest form a thumbs up or thumbs down to the production of a specific generated output. And so you can actually do it yourself. If you go to ChatGPT, you can rate whether the generation is good or bad, right? And so this is what human-based reinforcement learning is all about. Is where humans come in and judge the text that is being produced by the large language models. It is difficult, but also it's ethically difficult. And I hope maybe some of my colleagues are going to talk about that later.
Is it scalable?
Is it scalable? It is scalable in the sense that it will create more jobs. And I think that is important. No, I mean, I'm completely serious here, right? We are creating a new industry. This is a new industry, and we are creating new jobs. And it's important to understand that these are jobs. The same way that computer scientists, software engineers 20 years ago were unpaid because they were just IT people. Today, we know that software engineers are important people because they create the software that we base everything on. Same thing for human-based reinforcement learning.
You said that language models just predict the next token.
Mm-hmm.
And you gave the example, would this movie review is positive or negative?
Mm-hmm.
I love this movie. And I don't know if I understood your play, but you said that it will just continue the review.
Mm-hmm.
But I actually live-pasted it into GPT-4, and it's actually said this is a positive review. So it didn't answer the question. I guess my question is about emergent behavior,
Mm-hmm.
right? Because maybe this is all you need, right? To predict the next token is all you need to create human level AI.
Mm-hmm.
Or some superhuman.
So I think we need to distinguish. I had this discussion twice the last day and a half. I think these models are reactionary. So they react to something very immediate, right? So the text that you put in, they don't have this capacity of like deeper level thought. And there is processing to sort of like instilling that knowledge into them. But that's how we as humans work most of the time in our days. We make decisions all the time. I make a decision whether I'm going to answer to you and when I'm going to answer to you. That's a reactionary decision. So if we can approximate those reactionary decisions fairly accurately, that's a good enough system for most of the applications that we need on a daily basis. So that I would say is good enough. Yeah.
There is a question from the virtual part, and the question is about reproducibility. It seems that in effect these models are inherently stochastic and cannot be forced to be deterministic. So there is a reproducibility problem. What do you say about this?
I say that the reproducibility problem starts with the fact that if you want to train this model, you probably need a high performance computing infrastructure. So obviously not everyone has access to that, and not everyone wants to put that creating these models in the first place. It doesn't make any sense to create a new model every 2 days. It's only useful, these models are only useful if they get used extensively. And so that's the first problem, that reproducibility as a nice concept starts clashing with the reality of burning trees, because that's what we're doing when we're training these models. And the second part of reproducibility for other applications, for instance, for downstream prediction tasks, that may be more addressable, yeah. But because they're gated behind companies, sometimes we don't know exactly how they're modifying the models in the background. So that's obviously another problem. But if everything is open, I think they are reproducible. They would be reproducible. Bloom is a good example of that.
One more question.
Hi, thank you for the talk, very interesting. I was wondering, you touched a little bit, but these models don't really have critical thinking.
No.
So using ChatGPT as a user, I noticed that, you ask certain questions and you get answers like, I'm only an AI, I cannot really give you medical advice, or, this is an inappropriate question, I cannot judge that. How does that technically, has that part of the model? Is that something you do afterwards in like the user interface, or is it actually in the model?
Yeah, that's the software enterprise on top of the large language model. So absolutely, that's guardrailing, that is creating solutions where it's not you're not hitting the model first, it's the last thing you hit, right? Okay, first you hit a lot of checks and balances and bias and other things, maybe other language models that sort of like decide, is this a good prompt or not? And then you go to ChatGPT. And then even after you go to ChatGPT, there's adjustments. For instance, there's systems which are retrieving data from databases because these models have been trained up to a certain date, and then they need to be updated with new knowledge, right? So there's a lot of adjustments to the model in the application of how we use them. So large language models are useful, but if you put them in production, you need to do all of this software engineering on top of it.
One more question.
Hello.
Hi.
Do you think that the process of scaling up the large language models have the potential to create general intelligence models or godlike intelligence, or new features will have to be developed?
Interesting. I wish I don't even have a PhD. So personally, it's my personal position. No, I don't think we're gonna get to general intelligence with just large language models that are predicting the next sentence. Again, what do you define as intelligence is my question. The long answer is, if we combine it with software engineering, yes. So I think we can get to a place where it can approximate a lot of intelligent behavior, but it's an approximation. Real intelligence is probably a different question. Yeah.
All right.
Thank you.
Sorry.